Welcome. All right. So, welcome to the 2024 AI Summer presented by Vanderbilt Data Science. I'm so glad that you're here. I'm Jesse Spencer-Smith, and I'm Chief Data Scientist and Director of the Data Science Institute at Vanderbilt University. And I'll be presenting today and on Wednesday of this week. And we'll be talking more about the course in a moment. But first, let me go and call on other folks who are with us right now from the Data Science Institute. Let's start with Abby. Would you mind introducing yourself?
Hi, I'm Abby Petulante. I'm a postdoc at the DSI right now, and you will likely hear from me in later weeks, maybe giving you some material.
Absolutely. And just so you know, Abby and the other data science postdocs and data scientists at the DSI, we love to get questions. You're going to be hearing about a wide variety of projects that we've undertaken. So some really good experience for you to draw on in your work. John, would you mind introducing yourself?
Yes, absolutely. Hi, I'm John Ellis. I am an administrative assistant with the Data Science Institute. I am very new to the role. I'm very excited to get to join in on the summer course. I'm really excited to gain a firmer grasp on generative AI systems and to broaden the scope of my understanding of what I'll be working with. I'm really excited to take part in this with you guys.
Excellent. Thank you. Miguel.
Hey everyone, I'm Miguel. I am the marketing coordinator for the DSI. I help out with all digital marketing, events, and social media. This is my first time being around for AI Summer, so I'm very glad you're all here, and I'm also glad to be participating as well.
And Amber.
Hi, I'm Amber Miller, and I'm the Assistant Director of the Data Science Institute. Looking forward to learning from everyone here throughout AI Summer.
Excellent. Thank you all so much. And the other members of the data science team will be joining us on Wednesday. Is there anybody else from Data Science Institute that I have missed? All right. So I'd actually like to start with a story before jumping into the description of the class and all of that. And so this starts with a presentation that I attended. So we had a visitor to Vanderbilt, a visitor that had done some really impressive work in chemistry, in organic chemistry, and in applying data science to organic chemistry. And I went to her lecture, her colloquium that she gave at the chemistry department. And this is let's see, up here, I need to pop all the way up to the top here. This is what I was greeted with. This was the first slide. I do not have a degree in chemistry at all. I didn't really even take much chemistry in college. I took AP chemistry, and that was kind of it. I did math. I did computer programming. I did those things. I did not do this. And this was the first slide. And I'm thinking, man, I'm going to be getting absolutely nothing out of this talk. This was followed by the second slide, by the third slide. So I decided to see what I might be able to do, because I keep on talking about how generative AI is not just a tool to help you write. We think that because it's generative, so it helps you write. Actually, that's one of the weakest uses, frankly. Instead, it can help us understand. So I always talk about people being augmented by generative AI. So I decided to go ahead and put my money where my mouth is, and to see if it would be possible for me to actually understand what was happening in this talk in real time by using generative AI. And so what I did was I went ahead and I spun up my chat GPT on my phone. And I'm going to pull it up right now. I'm going to show you exactly what it looks like. So this is the actual session that I had just about 2 weeks ago. And what I did was I took a picture of the screen. As you can see, it's not a great picture, right? It's from the side. It's not straight on. and I began to ask questions. So I took a picture of the slide, and I just started with, what is DFT? And okay, DFT stands for density functional theory. Notice that the only way that it would have known what DFT was without additional context was by using the image. So the image provided context for what I meant by DFT. It goes through, it gave me an example, it gave me a write-up that actually helped me understand. That was terrific. So I took the picture of the next one. Now, this is real time. She's talking, I'm taking pictures, I'm listening to her, and at the same time, I'm taking pictures and reading what ChatGPT has to say. So explain this to me. I'm a data scientist, not a chemist. So now it goes through and talks about the research program that she has. And right around the same time that she's saying, so here's our research program, ChatGPT has come up and has said, the slide presents a research program, experimental data, property collection, quantitative prediction, MLR analysis. These are all things that she talked about, that she started to talk about, that ChatGPT was able to get from the image directly. Then here's the big take home. They use computational chemistry to collect data on molecules, then apply data science techniques to produce the outcomes of chemical reactions. Now, this talk went on for a full 50 minutes. And all throughout, in real time, I was able to take a picture, ask a few questions, such as, here's the next slide. What's new in this slide? Right? So I'm not asking a particular question. I had taken a picture of the previous one. She threw up another slide. And so I asked, what's new in this slide? And then it describes to me in a way that I can understand. It's using terms like out of sample predictions using multivariate linear regression. I told it I was a data scientist. It knew that I would be able to understand that. And so it's used that terminology. And here's what's new. They're testing on new molecules. They have prediction accuracy. They have out of sample predictions. As I was going through each time, ChatGPT was giving me the information at about the same time that she was giving me the information, but giving it to me in a form that I could understand all the way through. So this was the very first time I'd been able to do this at this speed and using multimodal models. And I ended that colloquium talk being conversant enough to ask questions, being conversant enough. And so when I met with her the following day, I was able to ask her substantive questions. And also, believe me, I showed her this chat to make sure, I said, is this correct? And he went through, she said, yeah, oh my God, yes, actually, yes, this is great. So this is where we are now with generative AI. We're able to augment our decision-making. We're able to quickly go through and augment our understandings by the use of tools, multimodal tools, getting in-depth information in real time. This is the very first time in humanity's history where we've had this type of easy access to information. We've had Google, we've had search for a number of years, but now what we have is the ability to grab information, to grab context using audio, image, video, text, and then to have that pulled together and combined with other information in real time to help us learn, help us make decisions, all of this with an aim, all of this with the ability to augment what we're going to be doing. So tremendously powerful, tremendously important. What we're going to be doing during the AI summer is getting you to the point where you understand what the models are doing, broadly how they're doing it. And once you have that understanding, you'll be able to understand what the models are capable of and what they're not capable of now, and where the pitfalls are. We'll also be able to talk, and you'll have a good understanding of how to make good decisions about what models to use, how to use the models. And you won't have to take people's secondhand information. You're going to understand what's happening with the models. So before I move on to talk about the structure of the course, what questions do you have so far, either about that colloquium or about us getting started in the course?
I can ask a very quick question. Hi.
Yes.
So I was wondering how we should deal with the uncertainty with respect to what ChatGPT gives us as an output. Because
Mhm.
as a scientist, like I have worked on it, and there are many times when I read answers that don't really make sense.
Yes.
Not, I mean, they make sense, but they're not accurate.
Mhm.
And I guess that's going to be part of the course. I just want to throw out the question.
It's a fantastic question. So, first of all, let me ask you this, and I'm gonna let me share my screen. Well, actually, yeah, I'll share my screen over here one more time. So here we are with this, and this question in particular, and this question isn't just for you, but can be for anybody. How was the model able to answer the question? Tell me about, and I actually did this incorrectly. I should have said this next slide. I said the next slide, but it knew what I was going after. How was the model able to answer this question?
Based on the previous slides or the previous questions.
Right, right. So it was able to answer that brief, poorly worded question because it had the context from before.
Mhm.
Right? And think about that very first one that I had as well. And Sai, you're absolutely right. Context. Let's go to the very top one. When I asked what DFT was, DFT can stand for lots of different things. But because it had that slide image, it had tremendous context. So what you're going to be learning about these models, these generative AI models, that everything depends on context. If the model can be well trained, can have lots of information that it might have access to, but what it really comes down to is context. So how do you know that the model is being absolutely correct? That's tougher. There are ways to mitigate that, and there are ways to use it intelligently, and there are ways to use it poorly. If you provide little context and no tools to the model, then it's going to be much more like a crapshoot. It may get things correct, but it's going to be depending on what it was trained on, whether your wording was all right. You're not going to, it's not going to be able to source the material at all. The more context that you gives it, like this, and this, there's a ton of information in here. I'll go ahead and I'll stop my share and I'll just give you a closer up view of the image one more time. There is a ton of context here. There's a ton of information here. So context is crucial, and we're going to be learning all about that. And proper use of the models is also crucial. But the main take-home message is, if there is more context, then the model will be able to answer your questions more correctly. But it's always going to be mitigation. And so it's always going to be an augmentation. It's very difficult. You have to be under very controlled circumstances to be able to hand over decision-making to a model. You have to have many safeguards built into that. So in short, the answer is context, and we'll expand on what that means in just a little bit, as a matter of fact. What other questions do you have?
Yeah, as someone who is maybe a little bit less familiar with the models, given that we're at the start of the course, what lens would you say it's going to be most useful for us to view the models through? Like as a tool, as a resource, maybe even as a collaborator that we're helping to make more, information available to it? Like what lens is going to be the most useful, would you say?
Terrific question. The answer actually is all of the above. However,
Mm.
what you'll be doing in the course, it in turns is using it in all of those ways. So, for example, I'm going to be giving some homework later on today, and I'm going to be asking you to tackle a problem that you've been working on, especially one that especially for the academics in the room, for the students in the room, one that involves multiple papers that you need to work with or book chapters. So I'm going to be asking you to engage with that, and that's going to be to assist you in discovery and decision making. But then later we'll also be using it as tools as well. And so we'll be exploring that as well. And so there's a question in the chat. What about the correctness of the information generated? This is what we're going to be talking about. So we're going to be talking about how the models work, and it is generative AI. And you're going to be seeing that if you provide context, and there'll be a number of ways to do this, then you can have verifiable information from the model, and you can mitigate the effects of incorrect information. So this is all about mitigation, or in particular applications, you'll actually be asking it to cite its sources. And in that case, then you'll be able to trust what it has. Where I would absolutely not trust the models is if you give it no context and you treat it like Google. Then if the model has been well trained on that particular kind of information, it may be fine. But if the model has no access to tools, and I'll be describing what that means, is the information correct? What was it trained on? Correct information? Did it understand your question correctly? It can't cite its sources if all you're doing is asking it to act like Google. So one of the things we're going to be talking about is sort of the highest, best use of the models and where it is appropriate and where it's inappropriate to use. But yes, that's absolutely something you're always going to want to be conscious of.
Could I ask a question?
Please.
I'm a mathematician, and so work with equations and data and stuff, and I'm kind of fascinated by the transmission of the information in that picture into
Yes.
the program. And I mean, that really seems very spooky.
It's, the lovely thing about this is behind the scenes, it's all math. It's math all the way down. But the other thing is we tend not to appreciate the power of distributional representations. And it turns out that is the core of this. And we'll be getting into that a bit, but know that that really all the way down is, and we're gonna see this in a moment, is all we have is a powerful learning algorithm. And we have different ways of training it and different ways of using it. But at the core, a powerful model which can learn distributional properties. That's kind of it. So what we're going to talk about next then is how it can learn and how we're able to train it. And also, Philip, know this, there are models that have been specially trained on mathematics, some areas of mathematics, for model theorem proving in particular areas. But know that you have a powerful general purpose learning algorithm, then that's something that you can do additional training on. So think of it again as augmentation, not necessarily great at going out on its own, but terrific when it's guided by the context that you give it in order to solve certain types of problems. One of my favorite things to do is to take highly disparate areas and to see if there's a way to sort of pull it together. So I've done in the past, I've done some work in different geometries like Alexandrov geometries, and I was, I put in a paper about that, and then I put in a paper about transformers and attention mechanisms that we're going to be talking about, and had a conversation about how I might be able to use the ideas from mathematics to understand this a bit better. And the synthesis of that information together was really enlightening. It couldn't have done it without me, though. It didn't. There's no reason to put those two kinds of things together, and so we're the crucial piece to actually provide the context in order to do this creative work.
So if in that first slide, if the DFT wasn't there and you asked it that question, what do you think would happen?
You know, that's a great question. One thing that we can actually do is actually just erase that from the slide and try it out, which is the other thing. You get to experiment with this as well. So I will absolutely try that. We might try that during office hours.
Okay.
Excellent. All right, folks, let's talk a little bit about the course. So this is AI Summer. We are going to be meeting Monday, Wednesday, Fridays on most weeks. We're not going to be meeting on Friday this week because it is Vanderbilt's commencement. I'll actually be Marshall there, so I'll be all dressed up on my regalia during the time we would normally be meeting here. I'd like to ask you to take a moment to rename yourself. If you're in a lab or if you have an affiliation, we're going to be doing breakout rooms a lot in this. So when we set up the breakout rooms, we want to put people who are all in the same lab who'd like to be together. And we'd also like to put other folks that might want to hang together as well. Otherwise, we'll do it randomly. So here are a couple of what I'd like you to do with your name. So I'm gonna show you with my name right here. I'm going to rename myself, and so I get always put into the same room as other people from the Data Science Institute. So notice that I prepended my name with DSI-. And that's what I'd like for you to do. If you're in a lab and you'd like to be in the same breakout room with your lab, go ahead and put your lab name, keep it short if you can, dash, and then your name. If you are joining the Data Science Institute as a master's student, or if you'd like to hang with other Data Science Institute folks, go and do like I did, DSI-. If you are interested in hanging with other faculty, because we have faculty members, we have postdocs, we have staff, we have undergraduates, and sometimes faculty like to sort of talk about how they're going to be using generative AI in their class, then please go ahead and put faculty-, and then we'll put you all together into the same room. So any questions about prepending your name? If you don't have anything to prepend your name, great. We're going to put you with other folks for you to be able to meet with. Any questions about prepending your name?
So this is a Zoom function.
It is, and the way that you would do that is you would do, it's called rename. And you can click on the three, I think you can click on the three dots right above your image. John, if you could take a look and because I'm a host, so my view is a bit different. Did you see it, Philip?
Yep.
Excellent, great. All right, I'm going to give you all a chance to do that, and then we're going to start setting up the breakout rooms in just a moment. The other thing I'd like to do is I'd like you to feel free to, just like you're doing, raise your hand. Oh, Maggie, thank you so much. Raising your hand when you have a question exactly like that. So Maggie, first of all, what's your question? And second of all, how'd you raise your hand?
Oh, sorry, I accidentally raised my hand. So the
Perfect.
function is in the middle of the screen, the lower panel on the screen.
Yeah. And so if you all wouldn't mind, let's go and practice. If you wouldn't mind raising your hand, so everyone just raise their hand, and then you'll be able to lower your hand too. So this does a couple of things. For me, it puts people at the very top. And so it really brings attention to you. And if you do it by mistake, hey, you can just lower your hand. So let's go and use that pretty frequently whenever you have a question, or you can simply unmute yourself and ask. That's fine too. But those are really good ways to get my attention. Excellent. Very, very good. Let's see. What I'd like to do is I'd like to walk you through some of the resources that we have, and make sure that you have access to everything that you need to for a successful AI summer. So let's go ahead and let me pop over, and I'm going to share the repo with you. Let's see here. There we go. Perfect. So you all should have received an email, and in the email was a link to the repository. So this is the repository, and if you are if you did not get this, then go ahead and go ahead and do a message directly to Miguel if you could, and Miguel will send you another copy of the letter. Emily, did you have a question, or you simply hadn't had a chance to put your hand down yet? We're good. Perfect. See how well that works. So here is the repository. I'm going to make sure that I like to track what I'm doing here. Terrific. So here's the repository. And you're going to find all the resources here. This is always going to be under development. You know, we're going to be changing information as we're going through. But the README has really good information about AI Summer. If you don't have a lot of background with Python, it's still not too late. This week, we're not going to be doing programming a whole lot. And even later, you're going to see we're going to be doing AI-assisted programming almost all the time. But know that you can improve your Python skills with the information that we have here. The idea here is you use AI-augmented programming. Because the fact is, everyone here, everyone in the world who has access to generative AI is a halfway decent Python programmer. You just are. Congratulations. Because now what you can do is you can describe what you want to have done, have the model write code for you, and then actually be able to try it out. And we're gonna try that out either at the end of today or on Wednesday. You'll want to make sure that you get accounts, and it's a great idea to think about a project. You don't have to have one. We're going to have office hours. We're going to have our sessions from 9 to 11 each day, Central. And then from 11 to noon, we're going to have office hours. And that's going to be an opportunity for you to talk directly with us. And it could be about the class, or it can be about other things as well. But if you have a project in mind, it helps. You don't have to, but that helps you sort of focus what you're doing in the workshop. We are going to have sessions over 4 different weeks, as I mentioned, Monday, Wednesday, Friday, except this week it's only going to be Monday, Wednesday. And we're also going to be skipping Memorial Day as well, so we'll only have Wednesday, Friday on those days. And generally, this is going to be an introduction today and Wednesday to give you a directionally correct understanding of the models and actually learning how to use them as tools. There's going to be really essential information that we're going to be talking about here. Second week, we're going to be talking about retrieval augmented generation. We're going to be talking about assistants, agents, and we're also going to have an introduction to diffusion models as well. Week 3, we're going to be talking about how to build AI solutions. And this is going to involve everything from running a model locally, training a model locally, or building a solution that you can share with others as well. We will have recordings of all the classes, and actually that will be listed right here in the repository as well. It takes a little bit because the processing has to finish on them, but as soon as they're done, then we will either make the recording available through Slack, and eventually we'll also make it available through YouTube as well. Maggie. Oh, nope, you're just, that's how easy it is. You can raise your hand, you can lower your hand. All right. We are going to be using breakout rooms. So breakout rooms, it turns out, is really a key part of this course being successful. So we break out into rooms of like 5, maybe to 8 people. And there are a couple of things to keep in mind for this. When we go into breakout rooms, and it will be to handle, different things. So the first breakout room that we're going to be doing in just a moment is going to be to introduce ourselves to one another. A successful breakout room, so you can actually meet other people and feel like you're part of a community rather than just on Zoom, is sharing your video when you enter the room. Even if your room's messy, put it on blur. Go ahead and share your video. It makes a big difference. Share your screen. So someone volunteered to share your screen and to take notes, and so everyone has something to respond to. And also be ready to share your screen to share what you found as well. So, everyone can share their screens, but be ready and willing to do that. We're going to have a document where you can actually put in your responses as well. And here, let me go ahead and I'm going to share the link for this one right now, as a matter of fact. So let's see, let me go ahead and get this AI Summer. Got to get you out of the way. So it's the breakout room document looks like this. And I have a reminder of what makes a successful breakout room right here. Let me go ahead, and what I'm going to do is I'm going to share this in the chat, and everyone's going to be an editor. So I'm going to copy the link, and I will go ahead and I will share that in chat right now, so you'll be able to get into that document. And I believe that we don't have so many people here, but I think we should be able to all be able to use that. So there's that document shared with you now. Yep, see a whole bunch of people getting in there. That's fantastic. So the way the breakout rooms work is I describe what's happening. So in just a minute, we're going to take 15 minutes. We're going to put 5 to 8 in a room. And Abby, if you can let me know just when you're ready. We're going to 5 to 8 to a room. We might get closer to 8. For this first room, I'm going to ask you to do the following. In 60 seconds or less, so keeping it quick, give your name, your area of interest or area of research, and share what you would like to do with generative AI. And go ahead and I'm going to ask you to put this. So let's say I'm in room 1. Then in addition to saying that, I'm going to put my notes in here. I'm going to say, Jesse Spencer Smith, typos are fine. Doesn't have to be perfect. I'm interested in AI, and I want to build a personal assistant. So what this does is it lets me see all of your interests, and I can actually watch this in real time as this is happening. So I'm going to ask you to go ahead and put that in. You'll be able to tell which room you're in. If you happen to be in like the DSI room, go ahead and put that somebody put that at the top too, just so we can identify it as well. So there's going to be a lot of editing in here. So questions about the breakout rooms?
So one quick question is, how do I decide which room? I didn't catch this. How do I decide which room I'm in?
You'll actually be put into a room. I think Abby, you're sort of creating the rooms right now, right? Yep. So Abby is creating the rooms, and you'll automatically be moved in there. There'll be a timer, and then you'll always be able to pop out, if you want to, and we can put you back in as needed. Right. And Abby, how are you doing? Do you need a little bit more time?
Yes, I'm like 30 seconds from being done.
You're doing just fine. Let's finish taking a look at the repo. The report document is good for up to 100 people. And so that's here, come on, let's go ahead. And I'm thinking, how many people do we have in here right now? We have 81, so we're good. So everyone can be in there at the same time. This is some information just to remind you about the special breakout room groups. Remember to change your display name if you want to be in a special group. This is where the recordings are going to be. So we have our AI Summer playlist. We'll be updating that with the current AI Summer information after today. Below here are some course resources. Prompt engineering paper that some colleagues and I wrote sort of at the very beginning of ChatGPT. A really good prompt engineering Coursera course. Oh, that's misspelled. I'll have to fix that. By Jules White. And new from 3 Blue 1 Brown, a YouTuber and researcher that I really like, has done a series on generative AI, which is really good. And I'm actually going to be asking you to go ahead and watch some of those videos. It's visually, so it gives you a visual guide and sort of gives you the sense of how this works. If you want to dive in, if you want to know the theory, if you want to know the formal algorithms, if you would like to to be able to code one of these from scratch if you wanted to, because you understand the theory so well, you're welcome to take my DS 5690 course, Generative AI Models in Theory and Practice. Undergraduates, I'm sorry, you'll need to be a senior. The graduate students are welcome. I also regularly have faculty that join me that just sit in on the class. Always love to have faculty, postdocs, staff as well. So know that you are very welcome to join us for the class on the Vanderbilt campus. If you're Vanderbilt community, you can join me for that. Then we have other resources as well as you're doing work. If you're Vanderbilt person, we also have grants, compute grants. If you want to train your own models, you're going to see many models you can do parameter efficient fine tuning. You don't need big hardware for it, but sometimes if you're training stuff from scratch, and we'll be talking about that, you might need big compute. So all that and more is all going to be right here in the repository. The lessons are going to be in the form of Python notebooks that are up here as well. So everything you'll need for the course is right here. What questions do you have about the repository? All right. Then I'll share one final trick. You'll notice I always have my tea. So this is the sign when I ask a question, and I have this. This is take your time, put your question together, feel free to ask your question. I'm going to give you some time. And then if nobody has anything after a decent amount of time, know that then we'll put it away, because obviously no one has anything to share. But I won't rush you, but this is sort of the sign that you have some time to think through and to ask your question. Abby, how are you doing? Oh, please go ahead. Motion.
Yeah, hi Jesse. Question for people who aren't familiar with GitHub. Is a goal to, like, do we download this into like Google Colab and run it alongside, or
Yeah, we'll actually be
maybe?
going through that next week. But yeah, absolutely. You're going to
Oh,
see.
okay.
Yeah,
As
you're
long
going
as
to
we
see we
don't
have
need to know it now. Okay.
Exactly right. You'll notice this handy little blue button, and we'll actually have that on all the different notebooks that we have. And what'll be handy for you is if you get if you want to do a lot of compute, you might want to get a Colab Pro. It's $10 a month. That gives you some decent compute. But even without that, you should be fine for everything that we're doing. When we do some of the model training, you probably want to have a pro, but you don't have to. But you don't have to really know GitHub all that much, really. We'll be taking you step by step. Excellent. All right, so let's go ahead. I'm gonna ask us to. We're gonna get into our rooms for the first one. I'm gonna go and erase what I've done here because it's not real. Oops. There we go. I'm gonna go and delete DSI. I'm not gonna be in room 1, so I'm gonna go ahead and take me out of here. So we're going to go into our breakout rooms. We're going to do this for 15 minutes so you get a chance to sort of to meet one another. You want to, in 60 seconds, you'll notice the time doesn't quite add up, right? So I'm betting you're going to take more than 60 seconds, but keep it short if you can. Give your name, share your area of research and, or your area of interest. You might be an industry, you might be a student. What is your interest in generative AI? And share what you would like to do with generative AI. Go ahead and put that information in here. Abby, are we ready to start the rooms?
Yes, we are ready. And if I have misunderstood your prepend or something, just you can let us know. But I think also you should be able to move yourself manually to a different room if you need.
If you have real problems with the rooms, you probably need to update your Zoom client. So if you're finding that you're not able to do anything, you might want to hop off the Zoom, update your client, come back in, and we'll move you into the room as needed. All right, everyone ready? Okay. Remember, turn on your video when you show up in the room and unmute. See you all in about 15 minutes. Fantastic. And Holly, would you, oh, Holly, I don't think is here.
Yeah, I'm here. Would you guys mind? I'm gonna hop out. I just got in, and so I need to get myself a little.
Of course.
Yeah, thank you. I'll hop out for 15 minutes and then come back in. Thanks,
Okay.
guys.
All right. We'll see you.
Bye.
All right, folks who are still here, do you need, I guess we're all set now. Great. Abby, thank you so much. Amber, would you like to join a room? You can go ahead and put yourself in. I'm going to make you a co-host, actually, by the way. And
Okay. Yeah, I just had not gotten over to it, but I do see that there is a DSI room, so I will jump in there.
perfect. Sounds great. And Siyang? Siyang? Oh, actually, I don't think you're really here. And DB, do you need help getting into a room, or are you just an artifact? Okay, great. Abby, thank you so much.
Yeah, of course.
That would have been a real juggling trick to try to.
Yeah, it's always a little bit like to sort through all the different names. There's not like a lot of coordination between some of the labs, so it's like you have to figure out things go together. So hopefully I did it right, but
Yep, nobody's hopped out yet. Okay. Homework. Okay, let's go and take a look and see what people are doing. Oh, and is there a chat? Oh, when we come back, might need to can we just use Jupyter Notebook? We'll have to sort of ask and see what they're doing there. Okay.
I'm gonna take this opportunity to refill my coffee.
Good call. Ooh. Hmm.
Hi, Spencer. Sorry
Yes.
to interrupt you. Can I go to the room 5?
Absolutely.
Yeah, my colleague is there. Thank you.
Yeah, let me go ahead and. Room 5, there you go.
Thank you.
Right. And Abby, did we have a timer on this? Hi, Shireen. Hey, Abby, are you there? Did we have a timer on this? I'm may just be the new interface, but I'm not seeing the timer.
I believe someone was supposed to be sharing the screen for that, so I will go ahead and not mine up on the Google Doc.
Yes, I think Abby's getting coffee.
Okay. All right. And Umair, where are you finished up, or did you need to be put into a room? All right, I think I might go ahead and start closing up the rooms. It looks like most of these are finishing up. Hello, Katerina.
Hello, hello. How are you?
Doing well, thank you. Were you in a room or did you just join us?
Yes, I was in a room.
Great.
Yeah.
We're just about to close up the rooms then. Had we set a timer on these or?
Oh, no.
That's
I
fine.
don't-
Okay, great. I said I'd close the room about a minute because I'm seeing these sort of slowing down. So I'm going to go ahead and.
Gotcha.
I just sent out something saying closing the room in 1 minute. So I'm going to go ahead and close the rooms now. Welcome back, folks. Folks are still coming back from their rooms. We're going to give them just a moment to get landed back here. Folks are still coming in. I got to tell you, I'm so excited by reading all of these, all of the interests here in this document. There's so many possibilities here. So, and I'll just share with you before we actually get started. I've been teaching transformers at Vanderbilt in one form or another since 2020. And, you know, it's always been very exciting about the possibilities of it, but never have the possibilities been as broad as they are right now. So almost all the examples are really tremendously exciting. And I'll pick out some of these in just a moment. Max, I'm sorry you weren't able to edit the Google Doc. That may very well be. Sometimes, even though we're below 100, sometimes it doesn't allow editing, even though it technically is supposed to. So my apologies for that. And it will depend on when people have gone in. If we continue running into that, what we'll probably do is do multiple documents, and so we can have people all participate. All right, so take a moment. You can sort of, you all have a view of all the different uses there, wide range of possibilities here. And some of them are ones that you might not think about as being possible. So let's talk about transformer models. Let's talk about generative AI, because a lot of the examples that you're talking about here, that you mentioned here, are not using text. So people have talked about using this to analyze neuroscience data, recordings, field potentials, and spike potentials. There are people talking about full medical records, and they're talking about images and audio. So how is it that generative AI, which we often think about as being only text, can be used for these things? And how do the models get to be so good in the first place? So let's go and take a step back. What I'm going to do is I'm going to take you on just a little bit of a tour of where we've been, where we are, and how these models got to be at the level that they are. And we're going to be taking up the rest of our time today on this. We're going to do one or perhaps two more breakout rooms as we go through. But I'd like to start with a little bit of the history of where we've been, where we came from. Because we've been talking about AI for a long, long time. And frankly, there's been an immense amount of hype around AI. So actually, we've talked about it a long, long time. We first started to talk about generative AI back in the 1950s. So with a program called General Problem Solver. With General Problem Solver, the cool thing was you had computers, and you had we just started to develop programming languages, and here was a program that could actually solve a problem, solve a simple game on its own. Now you had to program it to solve that game, but at the time it was just this was human-like reasoning. It looked like to us, but it turns out you program to solve that game, it could solve the game, not anything else. It didn't generalize, and you had to think through all the steps, very painstaking. So then, 1960s and beyond, we started to explore the idea of a perceptron. Maybe the trick is to mimic human biology. So maybe you don't just write a program. Instead, you make something that looks like a neuron or a collection of neurons, and you see if you can't get that to act and to solve problems for you. And the idea here was you craft a perceptron, you craft the activation. So remember, with neurons, you have inputs into the neuron, and if it rises above an activation, then it fires. Same thing with the perceptron. And very interesting and a nice research topic, but again, didn't really scale. There was no way to you'd have to, if you wanted to get big, you'd have to handcraft, and the thought, trying to figure out how to handcraft a solution for complex problems was just well beyond what we were able to do. So then the idea came around, maybe what we need is expert systems. So you ask experts how they solve problems, and then you write down all those rules, and then you simply have a rules inference engine. Maybe that's the way to get something which is truly artificially intelligent. Well, a couple of problems with that. One is it turns out experts actually often don't even know how they're solving problems, especially if it's a visual problem or perceptual problem. Matter of fact, even with tasks, with a significant part of the population, so a significant number of you, if I asked you how you did long division, you tell me how you did long division. And then if I gave you problems to solve, you might solve the problems, but the errors that you would make would indicate that you were not solving it in the way that you told me was the way that you solve it. So oftentimes we don't have access to how we are solving problems. So systems were brittle. They didn't work very well. So that didn't go very, very far. Then came neural nets. So returning to the idea of a perceptron, the big addition here was a way to think about how to train these models. Rather than programming the models, you give examples and you train the models. This was a very powerful idea. It's called supervised learning. And the idea here was you create a system of perceptrons in a neural net. You use a process that's called back propagation. And so you yourself don't have to set those weights. Instead, we start with random weights, and then you have some supervised, you have some categories, and you have the model, you have some input. The model tries to choose the right category. If it gets it wrong, then you back propagate. Everything which contributed to the incorrect answer, you downweight. And if you do that enough, the model actually gets better and better at coming up with the right answers. Very exciting. I did some early work with this and it was terrifically exciting, but we couldn't get too large. We couldn't make the models very large because we had a problem called disappearing gradient. So if they got too big, the learning stopped. It didn't work. It's all the way back. It took way too much computation. It took hours and hours for these things to train. And we simply could never get beyond a couple of hundred, maybe a couple of thousand without completely running out of resources. So that also did not go anywhere. Well, a lot of interesting things, but this was not the solution to AI. So then around 2010 to late 1990s and then 2000s, now we started to get someplace with something that has been called machine learning, sometimes statistical learning. And the idea here is you take that idea of supervised learning, where you have categories. So let's go ahead and let's do a really classic example of customer churn. This was often, a lot of this borrowed from statistics and from different areas, but was used in industry quite a bit. Customer churn, you're a phone company and you want to know who's going to be dropping your service and going to another cell phone company. So you might collect information in a structured database. Here's the person's name. Here's the last time that they used your service. Here's the number of calls that they've made to you, help calls. Here's how long they've had their phone. Here's whether or not their phone is fully paid for, all this information, structured information they have about every person, and then you have the outcome. Did this person leave or did they stay? So now you have a categorization problem. Are they going to churn? Are they going to leave? Are they going to stay your customer? Well, turns out if you have that structured information, you can give this to various machine learning algorithms like random forest or gradient boosting. These are tree-based methods, or logistic regression, another way. And it would work really well. You'd need a couple of 100,000 examples, and then you can absolutely solve problems. Now, once you've trained a model to solve your problem, you've solved that one problem. You now have a model for customer churn. You can't really say anything about customer satisfaction. You can't really say whether or not someone is going to be upgrading. All you can do is predict whether they're going to leave or not. So an improvement, but still a lot of work. You have to come up with all those features. You have to program them in. And then when you do train the model, it can do one thing. Still tremendously useful, still useful to this day, but not really AI. So then around 2010, big advancements. So an ongoing challenge was vision problems. How do you take an image and do something with an image? You see how that looks different from the customer churn, where it's the structured information and the outcome? With an image, you might put a picture up there and you might say, what's in the image? Or you might say, identify this. Is a house? Is this a cat? You might have thousands of different categories. So how can you have a system that simply can take an image and then tell you what's in it? Around 2010, huge advancement in neural nets called convolutional neural nets. Again, convolutional neural nets. This again borrowed from human physiology. So we borrowed from human physiology when we started to use perceptrons and when we did neural nets. Maybe we can borrow from it again. If you want to solve something that's a vision problem, then maybe what you do is you make something that looks like the V1 visual cortex. And it turns out this worked really pretty well. So larger architecture solved the problems that we had back in the 80s with the disappearing gradient. We had much more compute now. Why? Because people started to play computer games. And so we had graphics processing units. GPUs turned out to be perfect for deep learning. Yes, they were originally for games, but it turns out that the matrix multiplies that you need to do to get a really good game and good graphics for a game are exactly the same kind of math that you need to be able to do convolutional neural nets. So now you had a system that was really pretty robust. You trained it on a set of images, and now what you have is you have a system which can now very nicely give you a pre-trained network that acts like a V1 visual cortex. In other words, it's been pre-trained, and so it knows how to see. So once a model has been pre-trained, now you can give it new images it's never seen, give it just a few training examples. Let's say you've trained on a whole bunch of data, but you've never actually trained on different types of mugs or cups. Never done it. So now you need is just a couple of dozen examples of these and say, okay, this is a tall insulated mug. This is a to-go cup. A couple of dozen of those, and now it can solve that problem. This is called transfer learning. So for the first time, we're able to pre-train and then do some additional training so it could solve other problems. Transfer learning using supervised learning for vision. But we still didn't have text. Most of the information that we have is tied up in text. We have a lot of information in images, but a lot of what we want to be able to these models to know is text. There was some early work with recurrent neural nets, but it didn't go terribly far. Until 2017, a couple of things came out. 2017, 2018. One, we had the first successful pre-training of a neural net on text. And second, a paper came out on a new way of dealing with text, which was not a recurrent neural network, but called instead a transformer, and used something called attention. And it turns out that this was very good at working with text. So now we had a couple of things together. We had something that could deal with images. We have something else that could deal with text. So now we really started cooking. So now for the first time, we can solve general purpose problems. We have transfer learning. But still, that doesn't fully explain everything that we're able to do yet. So what is different? What's changed between this time back here where we couldn't do much of anything to now I'm able to take a picture of a slide, a crummy picture, I might add, of a slide in a presentation and have me tell everything that I need to know? Well, a couple of things. One, transformers. Transformers are general purpose learners. So it's a new type of deep learning architecture, a newer type of deep learning architecture, different from what came before, that was a powerful general purpose learner. Turns out it could learn text and the information in text. It could learn images, learn sound. So it's a general purpose learner. Two, we started to use self-supervised learning. Let's pop back here for a moment. Remember, I mentioned convolutional neural networks. So convolutional neural networks worked because researchers had created and labeled millions of images. And so convolutional neural nets were trained through supervised learning. Turns out it's hard to do that with text. It's hard to label text in the proper way. So instead, what we do with transformers is we use self-supervised learning. We're going to talk about that in just one moment. Finally, we have transfer learning. You can train a model on text, and now it's able to do other things for you. So let me go and pause here. Let me go back to this image right here. What questions do you have about where we were and where we are now? John, and then Abby.
So if you had to sort of identify a really big goalpost, or maybe a better way to put it is an especially transformative moment on this timescale, maybe erring toward more recently, say in the past 2 decades. What would you point to as the innovation that sort of took it to the point where we're at now, where you can have a generative AI model as powerful as ChatGPT on your phone?
Mm-hmm. Yeah. So really, it is these three, the combination of these three things. With the powerful general purpose learner, that was the introduction of transformers and attention, the attention mechanism. We're going to be talking about that. We're going to be talking about a kind of a high level. If you want to get really in depth, I love that three blue, one brown. Three blue, one brown. The video, which we have linked in the repo, or also you can sit in on the class. But that powerful learning algorithm was one. But then we also needed to have this idea of self-supervised learning. You're going to see it's a very simple idea, but that's how we're able to train the models on so much data and have it learn. And third is that idea that it's key to have transfer learning. It's key to train on something prior. It could be the same information, but you're doing it in a different way. And then you turn around and you try to solve a different task. So we needed those three things. 2017, 2018 were tremendously important for that development. And that's really when things flipped. Abby.
So mine's just very basic. So the main difference between the convolutional, is that right? Neural
Yeah.
network and the recurrent neural network is the self-supervised learning, right? With the recurrent neural network, you don't need that.
So think of these sort of orthogonal, right? So convolutional neural net worked by sort of aping the V1 visual cortex. So you start with lots of connections, you narrow it down, you go to lots of connections again, you narrow it down. So it's the architecture that made convolutional neural nets different. Recurrent neural nets, what they did was they took information and they fed it back in the history. So it's recurrent. And so those were two different types of architectures. It turns out you can do self-supervised learning with pretty much anything that's a good learner. So that was sort of that's how these are sort of separate important ideas. Self-supervised learning, we could have used it anywhere so long as you had something that could learn.
Okay, so it's kind of thinking about it in terms of like a living network as opposed to a set one.
Yeah, so the actually self-supervised learning being the way in which we train, right? Versus an actual architecture. So convolutional neural nets, CNNs, recurrent neural nets, RNNs, and transformers are all different types of architectures. Whereas self-supervised learning is a way of training them. Amir. Oh, great. Is that it? Cool. Great. And Amir.
Yeah, very quick one. So seems like transformers have now solved a lot of the problems. Are there other kinds of models that are better than transformers? And what I mean to say is, if you learn transformers, would you expect a few years later something totally different to now take over?
So it turns out that there are some possibly alternative architectures, but there are going to be some principles that are going to be very important that'll sort of maintain throughout. So and I'm going to be talking about those. So transformers, I think that you will have alternative architectures, but they're going to have some things that are going to be very similar, right? So the principles, I think, are going to be the same. We're already sort of seeing movement outside of just pure transformers using attention to what are called hybrid architectures like Jamba. We'll talk about those briefly. But really, if you sort of keep it at the level of this, general purpose learner, probably transformer, maybe something that's related to that, self-supervised learning and transfer learning, those are the key things. Excellent. All right, well, let's go ahead. There's been huge development. Transformers, around 2017, 2018 here. And it turns out that there are multiple different architectures that are all transformers. The one that we're mostly concerned about is here under the decoder only. This is generative AI. You're talking about this gray path here, the decoder over here. We're going to be talking about what these different architectures are, but know that there's been huge amounts of development ranging from slightly different architectures to vastly different architectures to simply changing training. For example, this path right here, GPT-3 and Codex and instruct, and I might crash for just a moment, but I'll be back in just a moment. Okay, all of these resulted, these are the direct descendants to the models that we're using today. All of these have in common the transformer architecture. So that is in common between all of these. But sometimes the only thing which is different is the type of training that we give them. Okay. All right. Okay, are you all seeing my encoder-decoder transformer here? Fantastic, okay, good. Zoom is telling me that it's crashing, but it's doing so very gracefully. So I might fall off in just a moment. This is the full encoder-decoder transformer. This was the original one. And we'll talk about
I believe that is the crash he was talking about.
Look that way, yes. Seems stable enough, but was anyone else seeing like a small gray rectangle?
Yeah.
Okay.
Yeah, I saw that too.
All right, so that was okay. That was just, well, I'm sure I'll be back on in a minute.
Hi there, folks. I think my machine may have crashed. John, is that correct, that the machine crashed?
It's looking that way. You
Okay, great.
were stable there for a minute, but then you just cut out.
Okay, great. I'm going to go and reboot my machine, but I'll continue my conversation here. I'm on a loaner machine, which is not quite capable enough. So we're going to do a reboot here, and then we'll continue. Give me one quick moment. Okay, so we're going to do a restart there. All right, so for different transformer models, sometimes there's a difference in architecture, but sometimes the only thing that is different between the models is the type of training that they receive. The basic task that transformer models are capable of is the following, and this is decoder transformers. Guess the next word. That's it. Generative AI models refer to transformer decoder-only models whose entire purpose in life is to guess the next word. Oversimplifying a little bit, because actually what it's doing is it's generating a probability distribution over all possible next tokens. So let's unpack that a little bit. A generative AI model, first of all, like any deep learning model, can only take numbers as input. So this means if we want to put text in, we have to come up with a scheme so the model actually can just be given numbers instead of text. So one way to do this is that you identify numbers, you number all of the different words that you have. So, cat is 1, dog is 2, chair is 3. You can do that, but that results in a very large vocabulary because run and running and ran are totally different, right? They each have to get they each have to get their own numbers. So instead, what often will happen is that in the tokenization scheme, you actually have words. Tokens are words or subwords. If you have a word which is extremely common, then that word may get its own number. If you have a word which is not all that common, then it may be broken up into subwords. But know that that tokenization schemes are words or subwords. Okay. So that's one. Okay, I'm getting back on here now. So give me one quick moment while I pull this back up, and I'll get back onto Zoom from here. Here we go. So it turns out that that choice of tokenization scheme actually means a lot. Again, a quick show of hands here. How many people use GPT early and you use GPT-3 or GPT 3.5? How many people have started out using that back in the day, GPT 3.5? Go ahead and raise your hand if you did. Okay, so did anybody try to use GPT 3.5 with other languages? And how successful were you? If you wouldn't mind, because I'm a little bit constrained right now, go ahead and unmute, if you wouldn't mind, and share how well GPT 3.5 worked in languages other than English.
It was rough. That's all I got.
That's perfect.
Yeah.
What language were you trying?
Spanish.
Perfect. Here, one moment.
Terrible in Mandarin as well. Yeah.
How did it do with Mandarin? Oh, and how did the model do with Mandarin?
Not good. Not good. Well, not reasonable. Not translatable, actually.
So, any other languages other than Spanish and Mandarin?
I have tried Hindi. So we tried this for a project that we did.
Yeah.
And I wouldn't say it's terrible. I think it depends mostly on the prompt that you give. If you ask it correctly, it might give you like, I wouldn't say it's the best, probably like 50%.
Yeah.
It was okayish. So we just had to change the kind of prompt that we gave and we got a better result changing the prompt.
So here's the interesting thing. A lot of these problems boil down to the choice of tokens. It turned out that the early models, GPT-3, the tokenization scheme that they used was great for English, not great for other languages. So it took more tokens to describe, to represent words that were non-English. So a word that in English might be 1 or 2 tokens might be 8, 9, 10, 12 tokens in Arabic or in Mandarin or in other languages. So sometimes our models are different only because the tokenization schemes are different between them. So sometimes you can have exactly the same architecture, train on exactly the same documents, but if the tokenization scheme that you've chosen is different between them, one may work better than others. Fantastic. Give me one quick moment so I can pull up my slide deck for you, because we're going to go through and we're going to take a look at the architecture of transformer models. And as I'm pulling this up, any questions before we start going through the architecture of transformer models?
Very quick one. Sorry. So how does the system, the answer, as the answer is being generated, how does it know when to end? If it's looking at relationship between words, and you can have infinite set of words coming up, right?
Excellent, great question. Let's go ahead and walk through what this looks like, and let's think about and I'll pull up my slide here so we can actually sort of have a graphic to work against here. Here we go. Lovely. All right. So what happens when we use a transfer model is we put some word into context, right? This can be a question, a query, something along those lines. We have the token encoding, which is turns the words into numbers. And then we have this middle part here that we'll talk about in just a little bit. And then we have next word prediction. So let me ask you this. If all that it's doing is producing the next word, technically the next token, how do we get longer text out of it? Go ahead and raise your hand if you have an idea of how that might work. And Abby, your hand may still be up, but so Esra, how do you suppose that we get the model to actually generate text if all that it's doing is producing a probability distribution over the next word?
More specific prompts.
Okay. I think that more specific prompts is absolutely critical. Shane, I think you might have had your hand up as well. How do you, if the model is just producing the next word, how does it produce like continuous text for you?
I think you randomly select something from that probability distribution within a certain window. Some of the tokens could represent things more than words, right? So you can also include spaces or syntax or something like period, for example.
Yeah, but we still have the problem where it's just producing one, right? So if I'd say, tell me a little bit about, DFT. And the model comes back and the model says, well, Don?
Is there like a loop where the now well goes back and now that's the new input?
Yeah, exactly, right. And Shane, I knew that you were getting there too. Don, you're exactly right. This is called auto-regression. So you produce that next word, the next token, that's put back into your context, and then you rerun. How many of you, go ahead and just quick show of hands, how many of you have seen GPT-4 write and you sort of see it go fast and then slow? Yeah. It's not for show. That's actually the speed at which it is generating that next token, and you're actually watching it process in real time. So these models are called autoregressive models because it takes a step and then continues that and then goes through again. So it's adding to its own context when it's going through. Let's go ahead and run through and sort of see what this looks like. So we have a statement here, beware for I'm fearless and therefore, and then model goes through and it produces the next token. Anybody have a guess as to what this next word might be?
Powerful.
Powerful? Great. Excellent. All right. So it turns out that this property of generative AI is something that you can actually use to train it as well. So in other words, if you had given me strong, right, then I would score that as wrong. And what I could do is I could do back propagation. So back propagation, I would go and adjust all the weights up to this point that gave me the wrong answer. So let's run through this forward, and then we'll talk about what training of this looks like. So we talked about the context. It gets turned into text using the token embeddings, the token encodings. Then it's put into what's called a token embedding. So a token embedding takes a word, a number, and puts it into a high-dimensional semantic space. So a high-dimensional semantic space. And what that looks like is the following. I'll give you a prototypical example. So this is a high dimensional space. It could be hundreds, thousands of dimensions, but let's just use these three that we have available to us right here. So let's say that, and I'll use a prototypical example. Let's say that we have king. A king is a point right here in space, a semantic space. Now, it's a vector too. I can think of this as a vector coming from my origin all the way to where this point is, and that fully describes where this point is. And it turns out that point has meaning. Can you think of some words that might be sort of close to king? Yeah, John, what do you think? So what's might be close to king?
Maybe either queen or the name George.
Yeah, queen or maybe specific examples, right? Yeah, so queen might be over here. Yeah, exactly. So all those are sort of in the same space as king. Turns out you can do math too. So here, over here, this is, well, it's right here. This is man. Here's king, here's man. I'm going to subtract man from king. I'm just going to do math. I'm going to take the two vectors. I'm going to subtract man from king. Where do you think I am? And I'm sitting here now. What do you suppose is around king minus man? What are some guesses?
Like monarch?
Ooh, I love it. Monarch, right? Regent, ruler, those are all probably right around here. Okay, I'm going to do some more math. I'm going to go ahead and I'm going to add woman to monarch. All right, now where am I?
Queen and princess.
Queen, princess, absolutely. That's right. Fantastic. So an embedding is a vector which is in a high-dimensional semantic space. The space has meaning. So if I, for example, put cat, right? I have cats in there. If, then the cat could be near tabby, the cat might be near litter box, it's near things that are close to what is near catness. So the decoder stack. The decoder stack, this turns out to be the essential part of what's happening here. The decoder stack has two parts, and we're going to get more into these on Wednesday, but it has two parts. One is the attention mechanism. So this is where attention goes in. Attention is in each one of these stacks. So part of this is attention, and part of this is a feed-forward network. And you can think about this in two different ways. The attention mechanism allows all the tokens in the context to communicate with one another. And the feed-forward network further informs and enriches the embeddings. So here's the sentence that I'm going to give you. I want you to help me to sort of think through it. The cat took down the gazelle. So tell me, when I first started that token embedding, I put cat next to litter box. Does cat actually belong next to litter box if the sentence is the cat took down the gazelle? No. As a matter of fact, if you put a litter box out for that cat, the cat wouldn't know what to do with it and would probably eat you, right? Different kind of a cat. But the only way that we know that is from the context of the cat took down the gazelle. So that means we need to have communication between the tokens to know what kind of a cat we're talking about. And took down, what do we mean by that? Like notes? No, like grizzly, right? So all of that, this communication within that context is important to inform where each of these embeddings should actually go. Then we need to enrich that. So we may have the cat doesn't belong here, over here near the litter box. Maybe it needs to move over here to a little bit closer to wild animal, dangerous. So attention moves that around, moves that closer to where it should be. And then the feed forward network further enriches it. So if this cat now is closer to dangerous, right, and wild, now when we do the feed forward network, that embedding, that embedding for cat is now going to be imbued with additional meaning like savanna, perhaps Africa, alpha predator. All of that's going to be included and enriched into that embedding. Remember, the embeddings are vectors in a high dimensional space. The embeddings have meaning. We can add meaning to these vectors by combining them across a context and by enriching them in that feed-forward network. And each decoder stack has both an attention and a feed-forward, each one. As this goes through, you get more and more refined representations until you get to the end, and that's when you say, okay, what do I got? Let me make my next word prediction. John, you have a question?
Yes, this might be kind of basic, but I just want to make sure. So we're assuming that this network is operating in a pre-existing semantic space, right? Not one we've had to generate. Okay, that's what I thought.
But great question. Where did it come from? Like, this came from somewhere, right?
Mm-hmm.
So all of these, what you're looking at here is a deep neural net. Remember that I said that way back in the 80s, researchers first described how to train neural nets using backpropagation. I'm going to ask you to go to 3 blue, 1 brown, and also have a conversation with ChatGPT about this. But you can use backpropagation to do training. So what are we going to train on, though? I mean, if we have to do supervised learning, that's going to be tough. So instead, let's do self-supervised learning. So what does that mean? That means I take a phrase, take a sentence, or take a paragraph or a page up to a certain point, and then I stop, and I say, guess the next word. Remember, because that's what the models are supposed to do, right? Guess the next word. And if it guesses wrong, I'm going to do backpropagation. Everything in the network that was responsible for that wrong answer gets downweighted. And remember, this is the way that deep neural networks learn. It's called backpropagation. We're going to see what that looks like. And actually, yeah, we'll do that momentarily. But so the trick first, though, is learning off of the words that are missing. So what can you learn from words that are missing? What do you need to know in order to get the right word? Because that is what you can learn. So here, I'm going to show a phrase. I'm going to ask you to, in the chat, type down the very first word that you think of. If you've seen this before, please don't put a word in. The challenge here is that I'm going to push you, and I want you to respond and start typing immediately. And actually, let's go do the following. If you can, be ready to start typing, have your chat window open, start ready to type, because I want to push you before you have a good answer. So start typing immediately the first word that comes to your mind when you see this, because what we're doing is we're probing your deep neural net to see what that early processing looks like. Okay, you ready? I'm going to flash it in front of you, and I want you to start typing in chat. Everyone has their chat window? Okay. I'm going to flash the word. I'm going to flash the phrase. I want you to guess the missing word. Ships at a distance have every man's wish on blank. Fantastic. Okay, great. Oh, these are great. These are wonderful. Okay, couple of things I'm noticing here. Everyone, and all of these answers are nouns. How did you know that it needed to be a noun? And
it was one word, I think.
Yeah, so it needed to be one word. Absolutely. Could have been a verb. Could have been anything.
Go
ahead.
Oh, it followed a preposition.
Ha ha ha. Right. You may not have been able to think about that at the time, but now looking, it's like, oh, it's the object of a prepositional phrase. It needs to be a noun. So you knew that it needed to be a noun. Okay. All of the words that you had something to do with wishes, or with being on the ocean, or a ship. How did you know what words had to do with the other words in the sentence. You knew about ships, right? You knew they floated on water. You knew that if you're at a distance that you would be near the horizon, maybe. You knew that wishes go with command, so that might be that. So you knew the semantics of the words in the sentence, and you knew that you needed to be somewhere in that neighborhood. So let me ask you this. Which word should most inform what's in the blank? Is the word which is in the blank, is that have to do more with wishes or distances or ships?
Ships.
Yeah, right? It's on the ship. So you got to figure out, you have to know. So think about everything you have to know. It has to be nouns. You have to know language rules. Second, you have to know semantics, because you have to know the other words that are associated with the other words that are in the sentence. Third, you have to know which part to attend to. This is where attention comes in, right? So which part is most important? And finally, we had two answers that I saw. One was on deck, and another one was on board. Ships at a distance have every man's wish on deck. Ships at a distance have every man's wish on board. How many people like deck? Raise your hand if you like deck. Okay. How many people like ships at a distance have every man's wish on board? Raise your hand. A lot more people like that. Let me go and ask real quickly. Everyone who took their hands down so quickly. Let me go and ask Emily. Did you like on board better?
I think so.
Yeah.
So.
What made you sort of lean more to ships at a distance have every man's wish on board versus deck?
So I think I use an activity like this in my reading comprehension class with my own students. And I think it sounds more natural to me. It's probably what I would find as a co-location more likely. So I just like the way it sounds.
Yeah, could be more likely. Absolutely. More natural. That's interesting. Tara, what drove you to on board versus on deck?
It was actually the same.
Oh, go ahead.
Can you hear me?
Yes, go ahead.
Okay. It was actually the same thing. It just was more natural. I would never say in that case, on deck.
So it sounds better. It's better writing, right? And especially because we're talking about wishes. We're obviously not really talking about all hands on deck. We're not talking about the poop deck. We're not, no, we're talking metaphorically. Zora Neale Hurston was absolutely writing metaphorically. And so think about, and it turns out, here you go, the answer is on board, right? That's the actual answer. To get that right answer, you have to have learned parts of speech, semantics, where in the sentence to attend to, and writing style, which means all those things are learnable from simply leaving out a word. And it turns out this is the key to training these powerful general purpose learners. Self-supervised learning is leaving out part of the signal. So the model is forced to use all the other parts of the context in order to unravel the mystery of what that missing token was. Sometimes this is called causal training because it's the last word in the sequence. Other transformer models, you leave out other things. You can train them in different ways, but transformer models, generative AI is leaving out that last word, and it can and does learn all of those things. It learns about ships. It learns about writing. It learns about semantics. It learns about parts of speech. And you know what? It doesn't matter what language it is. If you have enough of a language, it can learn it. It doesn't matter what area it's talking about, science, humanities, religion, it can learn all of it because it learns the powerful general purpose learner of And now we have self-supervised learning, and so the model can learn anything, and we don't have to do a whole lot of work. We're simply leaving out part and say, figure out, given the context, what that final word is. John, you had a question.
Yes. So I think in sort of both responses, it was a feeling of naturalness, and I would agree that's where I landed, was bored. It was almost rhythmic, like every man's wish on board. But for the system, at that point, is it more a matter of likelihood? Like we were talking about. No, okay.
Well, I mean, I'd want to make sure that when we say likelihood, you might be tempted to think that it's just which one occurs more in the context, right? Just give me the word count, which one shows up more. But that's actually not the case, because you can give it a sentence that has never been written before, and it can still do the task. So it is more likely in the sense of probabilities, given the probability distributions, right? It learns the probability distributions of languages. So this is beyond counting. This is more, the easier way to think about this is in a Bayesian framework. Here's the thing to keep in mind. Distributions are information. So the model learns the distributions of words given other words, but really what it's learning, it's gaining information that's being carried in the signal, which is the combinations of words. So it is learning about the semantics through distribution. So yes, it is one which is more likely, but not in the sense of the frequentist sense of what occurred most in the past, but rather, given this rich distribution, this information, given the information they have in the context, what is most likely given that information? Does that make sense?
Yeah, I think so. So it's a little bit more of an if-then.
A kind of. We'll get back to this a little bit more too. Chinon, you had your hand up? And Chinon, did you have your question? Okay. Tara, did you have a question?
I did actually. So, of course, I couldn't just stick to one word because my brain took distant and wish as the key elements. And so in prompt engineering, how do I get around that if I wanted the horizon as the answer, but that's not how my brain works? How do I get around that? Are there rules I can learn?
So absolutely there are. So now you kind of know how all of this works, which is, and here, I'll flip through this just so we can get the idea. When it comes up with the wrong answer, then it does back propagation. It changes the weights. We're not going to get too much into it right now, but know this is a deep learning network. And so each time it makes a mistake, it changes and modifies and refines that network. And so then it can get the right answer. So prompt engineering is the practice of devising prompts, this context, such that you get out of the model what you would expect. And we'll be talking a little bit more about this on Wednesday, but what it all comes down to is the response is more likely given the context that you give it. So if you say, if you describe well what you want to get out of it, then you're more likely to get that thing. And we can actually do additional training on this network, and so it does a better job at things. So if anybody says, and I want my output in JSON, right? The CS folks or other folks may know, JSON. At first, the model may not be very good at it, but if you give it additional training, so that if you ask for JSON and it gives you anything but JSON, you train the model further, then the model gets better and better until you might have a new version of the model, which is now better at producing JSON. So the model announcements that you see frequently that, oh, now you might have remember from a couple of months back, Llama 2 code was a special version of Llama that was trained on much more Python code. In exactly the same way, here's a program missing the last word, the last token. And so it got more and more training to get better and better at coding. So the models are trained on billions or trillions of different tokens, words, right? So huge amount. But then you might give it special training so it does your particular task better. It turns out there are ways of training models, and so it can do better for your work. We're going to be talking about that in week 3. And it all looks like this. So you can either train a model to work better for you, or you can get better at prompt engineering, how you ask for things and how you state things. And so the model will respond better and more appropriately. And it all has to do with providing better and more context for the model to be doing its work. So the Coursera course that I mentioned, the paper that I link in the repository is a very important one to read. The Coursera course is a great one to give you better skills on having the model respond in the way that you would like to have it respond. Does that answer your question?
It does. Thank you.
Excellent. Very, very good. Let's go and take a quicker look in here. I mentioned that in here, in the encoder stack, they have these different things. This is that multi-head attention, and this is the feed-forward network. The idea here is you have these embeddings that are flowing in. So from this point forward, token embeds all the way until you get to these hidden states. These embeddings flow through, and they're getting more and more enriched as they go through the encoder stack. So by the time you get to the end of it, cat isn't a tabby. Cat is a dangerous, for us, wild alpha predator that lives in a particular area. We mean that kind of a cat. And all that happens incrementally as the information flows through the network. And now you can see how all of this is important. If the token encodings are not great, then you might have 6 different tokens together, which are representing cat. It gets really difficult for the model. It can do it, but it's a lot more work to tie those things together and then to come up with a richer representation. So tokenization is important. Training of the network is important. The text that you give it is important as well. Mohsin.
Yeah, thanks. So just to be clear, there's no feedback mechanism right yet, you're saying here. You're saying it somehow learns in this forward process that we're talking about a lion rather than a tabby?
Yeah, so let's go ahead and break these two things apart. When we're doing training, and here we're doing training, right? This is the backprop. This is effortful. This is very expensive. You're going to learn how to do this, but it's going to be a special type of training. But this is why the tech companies and why the not-for-profits spend millions of dollars sometimes to train these models, because it's so extensive to train this, right? When we are doing the cat, when we're going forward and we're doing the cat here, now it's just feed forward. It's cheap. It's a little bit, it's compute, but it's not that expensive. It's only feed forward. So if you're asking it to take a context and produce the next word and then loop it around to do the next one, no training is taking place, right? It's simply doing auto regression and is generating text for you. No training is taking place there. It's pre-trained and kind of ready to go. Does that answer your question?
Yeah, I get that. I'm just wondering because you said earlier that it learns through this feed forward that we're now talking about a ferocious cat, but that seemed to imply some sort of training.
Oh yeah, I'm sorry. I shouldn't have used the word learn. What I should have said is that the meaning is enriched, right?
Yeah,
So
I think that's what you said, actually. That's probably what you said.
Okay, good.
I'm trying to understand how it gets enriched just without knowing any feedback.
Yep. So you can think about it visually. And Alyssa, I did see your hand. So you can think of it visually. So think of cat starting here. But what's happening in this multi-head attention is you're literally informing and you're going to see averaging with the different parts. And so the cat took down and a gazelle. So now it's going to move that a little bit. And so now it's closer to wildcat and tiger and lion, right? And so it's moved there. And now we do the feed forward network, which is, oh, okay, let me put some more information about wild, dangerous cats in here. So now you have the new embedding and it's moved around a little bit more. And then you do attention again. It's like, wow, I really meant this. So it quite literally is moving through the space until it gets closer to what works with all the other tokens. All the embeddings are moving around, and then they get informed through the feed forward. No learning taking place, but definitely re-representing each of the embeddings from each of the tokens. First, they communicate with each other, and then the feed forward network, they're enriched.
Okay, that makes it better. Thank you.
Okay, great. And let's see, Alyssa.
Thanks, Jesse. This is a perfect follow-on comment from what was just asked. So it makes sense that you're adjusting the embedding space location of each word based on its context. And the context for each word is slightly unique, which is why they're not averaging together. But how is the weight, sort of the amount of attention to all of the surrounding words determined? Because, you know, you could, a very naive version of that would be positionally, like the words that are closer in the sentence to it. But we know that that's actually not how importance is done. So is there a way to model that? Or is there feedback on that? Or how does that piece happen?
That's a great question. And all of that is attention. So attention actually does a couple of things. One, it figures out, it does a weighted average. So remember before I said we could subtract, right? Oh, we're going to take king, we're going to subtract man from it. Well, it turns out you can also like take an average. You could take an average of the two, right? And you could do a weighted average. So cat is going to be probably kind of closer to gazelle than it is to took and then down, right? And so it's going to take a weighted average between these two vectors, quite literally a weighted average, more for gazelle than for took, right? And so you do a weighted average and it moves it in the space. It is incredibly simple in one way.
So Jesse, can I ask though, if I remember the sentence, took down is closer to the word, basically gazelle is on the other side of took down. So
semantically close.
So semantically close words get higher weighting.
Exactly. So the first thing is similarity. How similar are they in the semantic space? Then, if they're close, then the weighting is heavier. But all of these are learnable parameters. Through that back propagation, it's all learnable. We won't get into too much more detail about that, but there's a terrific paper which I will let people know about that gets right into the nitty-gritty of this. But know that these vectors are being averaged together depending on how semantically close they are, a little bit by their positional encoding as well, a little bit. So they get moved around, and then the feed forward network further informs that particular token depending on its new location, and then you do the same thing again. Excellent. All right, folks, we are getting close to the end here. My apologies, we got moved back just a little bit because my lovely loaner computer. So we're gonna have to hold off on the other breakout sessions, but we'll do that on Wednesday. Before we finish up, I'm gonna be sending out an email just with some homework, but it's gonna have to be a little bit later on tonight. So for homework, I'd like for you to try the following. One, I would like you to write a computer program in a language that you do not know. So if you know some Python, good for you. Write a program in Java. So think about something you would like to do. It can be any task that you want to, something you actually want to solve or something funny. You know, it could just be, you know, say happy birthday 100 times. That's what I used to write when I was first learning basic programming. Or it could be something useful. Work with an LLM to write the program in some language that you don't know. And then what I'd like for you to do is to ask for the LLM to describe to you what the program is doing and tell you about the syntax. And I want you to try a couple of things, giving more of a description versus less of description. And then I want you to see if you could actually learn from the LLM how you would run it. What would you need to actually run this code? So try that out and see how well that works. What I want to start doing, and we'll talk more about this on Wednesday, is using the LLMs as a tool as you're learning about generative AI. So Write a program in a language that you don't know. Second, take a look at the repo and do go ahead and watch that the video of that I mentioned before, the 3 blue, 1 brown. And you know, they don't take too long. You can speed through it if you want to, but it gives you a very nice visual representation of what's happening with the large language models. All right, what final questions do you have before we move into office hours for today? Yes, Michelle.
You mentioned that some of the videos would be on Slack. What is the name of that group?
Okay, actually, what I should have said was the videos will be on the repo, and we're gonna do videos on YouTube. It takes a little while for that to happen, so we might share the link to Zoom. To the Zoom videos as well. As soon as those become available, then I'll put those up on the repo, and then as soon as the transcoding is done, then they'll be up on YouTube as well. So it'll be on the repo. The links to the videos will be on the repo.
Thank you.
Absolutely, Ted.
Yeah, I have the meeting invite with the Zoom link, but it's only for today. It's not set to repeat. So my question is, will there be another meeting invite? Or
no, it'll be the same Zoom link. It's just
same Zoom link.
Yeah, it's just, you know, when I first created it, I hadn't said repeat yet. So
Yeah,
it's actually, it'll be the same one. Yeah.
Perfect. Okay, thank you.
John.
Yeah, so just so I understand, we're going to be having the LLM write the program and then have it tell us about it. Yes. Okay, that's what I thought.
Exactly.
Okay. Thank you.
All right, folks. I'm going to stick around here for open office hours. You're welcome to stick around, ask any additional questions that you would like to have. But otherwise, I will see you all on Wednesday. Have fun coding. Oh, and the link for the for the video recording is actually on the repo, so you can find the link to that there. All right, Ted, did you have another? Oh, Amir.
Yeah. So first of all, this was very informative. Now, with respect to ending the response,
Yes.
I could imagine even if there wasn't just one word for bored, right? That blank, it could have gone forward. And sometimes we see that ChatGPT is giving us answers that are way longer than is needed sometimes. So how does it decide at what point to end? Does it look at the information it's already shared with you? And yeah, like how does it come to that decision of where to end?
So you can do a couple of things. One, you can simply say, I only want to generate 10 tokens, right? And so it'll stop after 10 tokens. Or you can say, stop when you reach an ending point. So one of the things that models can do is generate an end of turn. So anyway, that's my answer, and that's all I have to say. Right? That's like, okay, that's clearly, now I'm generating an end of turn. So the models can generate tokens, and one of the tokens can be end of turn. This is where I would stop. So the model itself can generate the ending point.
But how do you know if that answer was sufficient? And maybe you do need the next sentence to clarify or something. You could have just ended there, but you did say another sentence after it to ask something else. You know what I mean?
Absolutely. And that is prompt engineering. So one thing that you can do, for example, one pattern for prompt engineering is chain of thought. So you could say, give me an answer, but first give me the reasons why you're going to be giving me this answer. Then give me the answer, and then evaluate your answer. You can say that to the LLM. As a matter of fact, that's one of the system prompts I use for some of the ones that I do.
I do that all the time, actually. I say, rate yourself or something.
That's right. And it's helpful too to especially the chain of thought before you get to the answer, because if you think about it, generation of tokens is processing for these. Remember, each time you go through, you're taking that embedding and you're enriching it, right? And then you're generating the next, that's processing. So if you ask it to do more generation before it gives you the answers, then you can have the model do better processing. And then in terms of when to end, if you have a specific task requirement, then you might need to do, and you can't get it quite with prompt engineering, you might need to do fine-tuning of the model, right? So it can give you exactly what you want. That's a problem with for example, creating JSON. Sometimes the JSON is terrible, so you give it a lot more training on that, so it can do better with JSON. Does that answer your question, Amir?
Yeah, thank you.
Okay, absolutely. All right, let's see. And I think next up is yes, Mohsin?
Yeah, I know I'm asking a lot of questions. If anyone else needs to ask questions, you can skip me. One of the things that I found from last year, your session, that really kind of switched it on for me was this notion of weights and what strategies change the weights and what don't. And you kind of serve 3 levels. And I'm just wondering if this is accurate, if I got it right. There's sort of the pre-trained models, which are like ChatGPT. And then you talk about fine tuning, so the weights are set with ChatGPT pre-trained, but then you fine tune it maybe on your set of documents or whatever. That also shifts the weights a little bit. And then the third way you can attack it is this prompt engineering, which doesn't change the weights.
So yeah, as a matter of fact, this was the very next slide that we didn't quite get to yet.
Okay.
GPT all by itself just generates the next token, right? That's what it's been trained to do. But GPT with instruction fine-tuning gets trained on a lot of tasks that have to do with answering questions. So the difference is this: if you ask GPT, just the base GPT, if you said, tell me about wild cats, then what it may very well produce is, because I think they're interesting. So what it's doing is it's continuing the question, right? But once you do GPT plus instruction fine-tuning, it understands that tell me about cats is a request. It's a task. And now it needs to respond to that task with an answer. And so now if you ask, tell me about cats to the GPT that's been instruction fine-tuned, it will say, certainly. Well, actually, no, it would say something along the lines of, they're both domestic and wild cats. Domestic cats, and then so on. And finally, you can do instruction fine-tuning plus reinforcement learning from human feedback, which would be, yes, you know how to do instruction fine-tuning, you know how to do a task, but now be chatty when you do it. Tell me about wild cats. Certainly. And then it tells you about cats, and it says, do you have more questions about cats? And that's the reinforcement learning from human feedback. So that's all training of the model, so the model has additional capabilities. Once a model, even if you just get to the point of instruction fine-tuning, even if you don't do the reinforcement learning from human feedback, now the model is ready to do new things. You can have the model do new tasks for which it was never designed because it understands how to follow instructions now. So you can say, I want you to play a game with me. And I want you to come up with all the different meanings of the word cat and describe them to me. The model was never trained on that. GPT would not be capable of that. GPT plus instruction fine-tuning could be capable of that. And so then when you have a GPT plus instruction fine-tuning, and especially the GPT with instruction fine-tuning and reinforcement learning from human feedback, that's like GPT-4, GPT 3.5 chat, anything that's called a chat model, you can ask it to do things. And in that case, then the more instruction and the more context you give it, the better it will be able to do, because it knows how to use that context now. Does that, Mohsin, does that sort of get in the neighborhood of what you were suggesting?
Yeah, I mean, that actually unpacked it even more for me, more than so I appreciate it.
Absolutely.
And so all of that is sort of, whereas maybe a year ago, we were just looking at maybe GPT plus instruction fine tuning, that was like, say, 3.5-ish to 4. And then the RLHF made it much more chatbot-y. But that's all still in the pre-trained, is that right? And then on top of that, we can fine tune it.
That's right. So actually, the big change, we've actually had generative models, generative AI models. We've had GPT since 2019, right? It's been around for a while, but it was when we did reinforcement learning from human feedback. Make your responses more human-like, be helpful, not harmful. That was ChatGPT, which came out, in 2022, at the end of 2022, and that's what changed everything. Because then you didn't have to like figure out how to phrase things and so it would do what you'd want. Instead, it was ready to do things for you and to be engaging with you as it was doing it. So that was a huge difference. And now we've gotten better and better at that, what we now call alignment, because we have things outside of reinforcement learning from human feedback. Now we have ways of aligning models, so they're better at doing jobs for us, and they're just getting better and better at that. And then you're right, if that doesn't work, you can fine tune a model to do a new kind of a task that was never trained for, and we'll be talking about that in week 3. Great. Amir, you had another question? And anyone can raise your hand.
Yeah, anybody please do. Okay. So as a neuroscientist who studies attention and cognition, I'm actually very interested in the way these models actually allocate attention. So what I would assume could be a good strategy is, let's say in the ship example, you had the words ship, distance, man. The cluster around ship, if you will, like the amount of space surrounding ship is a smaller one compared to man. And therefore, maybe in a hierarchical way, you would allocate more attention to ship because it's a smaller space. So you can be more efficient and then relating things that are related to ship, and then man would be the second priority, distance would be the third. Is that incorporated in any of the attention allocation?
So attention turns out to be really expensive, and it's specifically that part of figuring out how semantically similar each token is to every other token. So that's a matrix multiply, and you're talking about computationally big O n squared. So it's a lot. You have to multiply that whole matrix to figure out which ones are just close to. So if you could add more things onto it, like density, but then you have to calculate that. So it's expensive. So is it worth the lift or not? And we're going to be talking about this on Wednesday, but here's a visual representation of what's happening with attention. You can think of it as sort of blending the different parts here. So here's self-attention. So we have time flies like an arrow, fruit flies like a banana. So flies, in this phrase, flies is going to be, it could be close to arrow because arrows fly. So there's some overlap there. They're semantically similar in one way. So when we do the self-attention and it blends those meanings together, it's going to borrow more from arrow than from other places. Over here in this phrase, fruit flies like a banana. Well, in that case, there's going to be overlap with flies in the sense of, fruit flies. So that could be bananas. So you're going to be borrowing from fruit and from fly and from banana. So it gets more influenced by those. But that's a lot of math to do. It's important. We got to do it. But you go with what's close and then you average together and then you do feed forward and then you do attention again. So it's that cycle that you're going to be doing for however many layers you define. And it depends on how many layers you defined in your architecture. It could be 6 layers, it could be 30 layers. A little bit of enrichment versus a lot of enrichment. So yes, there are alternatives to attention. But really what you need is you need to have those two sort of elements, that communication across tokens, and then that enriching of each token using the feed-forward network. Those are the two important elements: communication in the context, and then enriching of each of the individual tokens using feed-forward.
Yeah, yeah, okay. Thank you.
Absolutely. Excellent questions. Other questions? Yes, Safika. And pardon me if I...
Yes, sorry if I missed this, but how does the communication between the tokens happen in a certain context?
So it's taking the vectors and averaging them, which to me, it's wild. It's like you literally are doing a weighted average. If banana is the closest thing that you got, then you're going to average that. And so now you have flies in the sense of banana, maybe other fruits. Now, if you do enrichment of that, it's like, what's fly near banana? It's like, oh, let's enrich that. Oh, that's a fruit fly. So that's the enriching of it. And then you do attention again, right? So it quite literally is doing the math on the embedding vectors to average them together. And each token, its semantic similarity to all the other tokens is calculated. Then you do that averaging, and then you feed forward.
Okay, thanks.
Absolutely. Other questions?
I have kind of a more bigger picture philosophical question.
Yeah.
One of the things they talk about is these things are great at generating responses, right? But they don't understand. That's something we have to remember as users. Like, there's not real understanding deep somewhere in the model. But I wonder where the line is, where the and what is understanding? What is it that we humans are doing differently on top of what it actually can do? And I don't know. Do you have thoughts on that and where answers may be?
So my PhD is actually in cognitive psychology and cognitive science, a lot of mathematical psychology. So I did mathematical models of cognition, of decision making. And one of my areas of interest was actually representational spaces. And my thinking was that the work at the time, there was a lot of processing that went on. You had these really heavy models that did a lot of processing. But the representations of the spaces were very simple. So, the cat took down the gazelle, for example. Cat had one location it could be. It was not influenced by everything else. This was cat. This was the embedding. And then all the processing tried to sort of deal with that in some way. And so, first of all, what we found out, or what we've realized now, is that representations and distributional learning carries a ton of information. It's different from us, right? We work with things interactively. When we can only attend to, our working memory is tiny. It's like maybe, 7 plus or minus 2. Literally, mine is much smaller than that. I have real difficulty with that. But we re-represent and we bring things down and we chunk, and we're always constantly revisiting. That's how we do it. This, on the other hand, is like a crystalline representation that frankly, I did not think was going to be possible using solely representation, but here we are. This is using only representation and a little bit of programming, a little bit of processing on top of it. So it's different from us, right? This is not human intelligence. This is a representation that is a useful representation that we can use to solve problems. So is there understanding? No, it's not active. Nothing happens unless it is generating that next token. But don't be fooled. Just by saying all it's doing is guessing the next word. Yeah, it's guessing the next word based on all of the trillions of words it was trained on. The knowledge that it represents, it knows, for example, that water expands slightly when it reaches freezing. Most people don't know that, but yeah, about 4%, and it will know that, it will represent that, right? And it can also account for everything in its attention, in its context. So we've been talking about really short context, but what happens when you get really long context? That means it has equal access to everything in there. That's something we can't do. It's a type of capability we don't have. So it's not understanding, but if we understand how it's working, then we can leverage it and use it to solve problems, even if it's not understanding, it's representing.
No. Well, I think to me the question is, it's not even a LLM question. It's more, what do humans do that is understanding? That's more on top of that.
Right. Which I love. It's really causing us to rethink, right? It's how do we do what we do? Is this, we call it an attention mechanism, but it's not attention like we have. Or is it? You know, they did the simplest possible thing, to blend information from multiple embeddings. Are we doing something similar? Or do we require active processing? We know that our learning is different. We don't do backprop because I don't know about you, but when I'm learning something, I don't have to eat 40,000 calories, right? I don't have to eat anything, but I can learn something. Man, if we learn through backpropagation what these models do, that would be immensely expensive, a huge amount of power. But we don't do it that way. We're doing it a different way. And forward inferencing is different as well. We simply cannot attend to all the things that it attends to. So there are things that are fundamentally different. So how do we do it? If we could crack how humans are able to learn so quickly, then that'd be a huge step forward. We're going to be talking about something a little bit later on called in-context learning, which is, I don't want to mention it. I didn't want to get into it now because it will confuse things a little bit, but it's an extremely powerful emergent capability of these models. That's fascinating. Anthony. Oh, and you are muted. Oh, Anthony, and you're muted. You'll want to unmute.
Oh, sorry. Yeah, good morning, everyone. I joined a little bit late. I'm an first MBA student at Vanderbilt. So I was getting lost on what is the meaning of LOM. So I searched online, means there's a couple of different meanings. So I don't know which. So maybe that will help me to understand what LOM is. And I understand the assignment also is on something on LOM. So
Absolutely. No, that's a great question. Let's go ahead and see if we can't figure this out. Okay, so let me make sure that this is, okay, great. I'm going to go to ChatGPT. Okay. Actually, I think I'll move this out of the way. So here we go. I'm going to go to my chat. So here I am. So try this. I arrived late at a workshop on this is on a workshop called AI Summer. They were talking, notice I'm giving it as much context as I can. They were talking about LLMs. What are these? I am a first or second year.
Okay, rising second year. So
okay, I mean, yeah, second year MBA student. Is that what you said?
Yeah, MBA, yeah.
MBA student. Please explain to me so I can understand. There we go. So notice a couple of things.
Okay.
Right? So a couple of things here. One, because it was AI Summer, it knew what an LLM was. It was talking, it knew that we were talking about large language models. And because of your background, now it's trying to give you information of how you might be able to use these, how this might be useful for you. Right? So large language models are trained on an astounding amount of information. They're driven by the context that you give them. And they are generating content which is informed by the context that you've given it and the training that it has. So as you're learning this, one of your best partners is going to be the AI itself. as you're learning. Other questions?
Thank you.
Absolutely.
The models are trained on the internet, right? Isn't that basically like all the content? Do you have any idea what percentage of the internet they're trained on? Just what order of magnitude?
So it was a big deal just a few months ago when models were trained on up to 1 trillion tokens. And that tokens are, words turned into numbers, right? Yes, it is pretty much everything you can get your grubby little fingers on the internet, whether or not it's licensed. Now open source models are very good about saying what they were trained on. And so they actually have a list, and there's actually available data sources now on which you can train your own model if you have enough compute. And it fully specifies everything that you can train on. OpenAI is not open about what they train on. Same thing with all the other big tech players. They're not sharing exactly how they do it. Meta, actually, with Llama 3, doing a much better job of making the models open and what they've been trained on. Now we're talking up to like 15 trillion tokens of training data, an immense amount of training data, which requires huge amounts of compute. We're talking about enough compute to run a small city for a number of weeks for the largest of these types of models. But yes, it can be
cooling all those servers, right?
Yeah. Oh, absolutely.
An aircraft carrier.
No, absolutely. So later on in the AI summer, that's why it's going to be so important for us to understand parameter efficient fine-tuning. If we want to do additional training of the models, and so they understand additional concepts or they understand additional tasks that we want to give them, then we want to be able to do that without having to spend $100,000 to, right? But it turns out you can take really decent sized models like the Llama 3 8 billion parameter. You can do additional training of that model on Google Colab Pro if you use parameter efficient fine-tuning. And we'll talk about parameter efficient fine-tuning and what that means. But it's a way of training the model with training just far fewer parameters, but giving the model great new capabilities. Philip. And Philip, you yeah,
going back to your original example, which I found fascinating, where you took the picture of the slide and it interpreted it. So suppose I don't know exactly about the training part. I mean, does a slide, if it's in PDF format or bitmap or JPEG, they're all different. They're all different things. Is it going to be trained differently?
No, great question. You could train differently, but often what happens is they get rendered, they get turned into images. And so it learns off of the images itself. So if you think about it, the same thing, and we'll talk about this on Wednesday more, but the same trick that we used with text, right? Leave out the last word, guess what the last word is. Oh, you got it wrong. I'm going to do back propagation. Imagine pictures. So here's a picture, but I'm blocking out this part of the picture, right? I'm masking it. Now fill in the missing part of the picture. So same kind of a task. Same thing with audio. It doesn't have to be spoken, right? So, if you have enough context, then you can absolutely guess what the next word in the sentence is going to be, right? If you have enough context, you can mask out the language, the sound as well, and have it fill in the missing sound as well. These are all signals that can be learned. So self-supervised learning with a powerful learner is a way that you can train these transformer models on text, on video, on audio, on, sky is the limit there.
There was also, I was listening to a podcast on AI, and there was a question about the collection of data, and the fellow who was talking, an expert, said that Tesla is the greatest data producer ever at the moment, which is, I find quite interesting and somewhat scary.
So Teslas are really interesting. So actually, I'm in Atlanta right now. I'm here for the Academic Data Science Association. And so I got here in a Tesla, but I didn't drive. It was in full self-driving the entire way. Except when I stopped for charging, then I took control actually for that part. It's transformer models, exactly the same type of architecture that we're talking about right now. That's what's driving the car, and that's what's handling the image from the cameras. That's what's handling also the control and the decision making. It's all transformers. Same kind of a thing. Here's a video of a good driver. You know, here's the controls, and here's what happens next. Learn what happens next. Oh, well, if you are driving and there's a person in front of the car, then the next best thing to do is to brake. You know, if you are driving and if a car is coming to your lane, then the proper thing to do is to move into the other lane somewhat. You know, so those are all things that can be learned through self-supervised learning, transformer model underneath. So yeah, they have a ton of data, and they do it in the following way. They both hold data, they've annotated a bunch of data, but now they're to the point where they want to learn something. Like one of the things that they need to learn, I'm on the latest version of the full self-driving supervised, is lane changes into left-hand turn lanes. It'll weave back and forth before it goes all the way into that lane. So it needs to learn that. So the way they do this is clever. They put out a call, if you opt in, they put a call out to all the cars and say, whenever you are in the situation where your left-hand turn signal is on and you waver, send me that. So the cars themselves will actually gather and they'll send that information, if you've opted in, when that has happened. And so now you have video of people correcting and say, God damn it, you know, so they correct the car, the situation that it's in and what's happening, so they can do additional training on that. Because training data is the name of the game. And using self-supervised learning, they have a huge server farm, huge, so they can train on the video, and so they can get incrementally better and better in the full self-drive.
So someday in the future, are we all going to be walking around with little cameras on it that's going to be sending data?
Could, if we want to. Already there's a push to have sort of assistance. And the idea here is models which can keep track of what you've learned or what you've said that you do, your emails, if you opt in. And, you know, think of it like an assistant that, because remember, these models have they can have long contexts. And so you can do things like ask questions against it, like, why did I walk into this room again? Well, you know, I would have remembered that you were looking to fix something before. You were trying to, you know, like my glasses, for example, they're very loose right now. So why did I walk into the room? Well, you were just fooling with your glasses and you were looking at the screws on the top. You were probably looking for the small screwdriver that's somewhere in the room. So that both that memory and that problem solving is something we could take advantage of. It's something that OpenAI is certainly promoting. I've been hearing quite a bit that agents and assistants are going to be a big theme this summer, which is making the generative AI models much more useful by using what's called agents, and we'll be talking about that, and also assistants which have this long-running memory, so you can actually recall previous interactions.
Thank you. Very good.
Absolutely. Other questions?
Thanks so much. Looking forward to the rest of the course.
Absolutely, Don. Thank you so much.
Thank you.
Absolutely. Thank you.
Okay, so I'll ask. So I am very new to all of this. Like I've worked in R before, but I've never really worked in Python. So if I'm going to revisit the tutorials that you posted, thank you. But is there any other suggestions you would give me as to how to approach this next assignment?
Oh, the assignment of write a program in a language. Yeah, write it in Python. Go and do it in Python. You know,
Okay.
think of something that you would have done in R, especially something you would know how to do in R,
Sure.
and give it like all the, you can even give it sample data. I'll see you. Give it sample data. Just give it right there in the context and say, hey, here's this data. Here's, you know, do the following in Python.
Okay.
And then ask it to describe how it did that, because using that, you can get a good sense of, you know, the Pythonic way of, you know, but this is something you can interact with. The more you give it, the more context there is, the more you can do with it. Here's a problem. I mentioned, I'm new to this. I program in R.
Sure.
Literally all those things. Here's a problem that I have. I know how to solve this in R, but I don't know how to do it in Python. So give it to me in Python. Now explain to me, how is this different? How do I need to think about, you can literally ask this, how do I think about this differently in Python than in R?
Okay.
Yeah.
Thank
You
you.
leverage what you do know. Anthony.
Hello.
Oh, Chunan, and then entails. Chunan.
Oh, okay. Anthony, please first.
Okay.
Oh, you go. I've asked a question before, so you go.
Yeah, actually I'm a very, very new learner for the data science. So I have a question, because you said we train the ChatGPT by use some Python or some Java data language, but it but if I don't know the Python, I think maybe I can use ChatGPT to help me, right? But
Yeah.
it's very, let me think, feel it's very strange. We try to train train the, how to say, the GPT to generate what we want to
Yes.
get, and so, and we ask it to give us the direction or the instruction how to use that kind of language. So I think, what's the logic of this training?
That is a so you can see here how to train a model, and I'm going to say, and your background is, you know, I'm an engineering student. Do you know Python? Do you know Python, Chunan?
Yeah.
Understand how to use Python to train a model, to train an I'm going to say LLM.
Mm-hmm.
Okay, and this isn't bad, but I'm going to go and say, take me through step by step. What framework do I need to use? Oh, here, it's doing it actually. Implement or use, yeah, see, this is it. So GPT tokenizer. So it actually will go through. This isn't bad at all. So this is a framework that we're going to be talking about all this, but you know, there's Torch. So you use a framework which is using GPUs. So you don't want to code this all on your own, these high-level frameworks. And it turns out that there are really high level and actually, you know, what is a high level level framework to make this easier? Oh, interesting. Hugging Face. I knew it was going to do that. So Hugging Face is a framework that will allow you to train models using far fewer. You know, I'm going to say, give me some sample code using to train a model using Hugging Face. I'm going to go and stop that generation and ask it for so you can see you can actually sort of get the guidance that you would need. That, along with the information that you have here, actually can give you what you need. So our job is going to be to describe what's happening generally, and then you can get the specifics that you need, between the models and the documentation. Does that answer your question?
Thank you. Thank you very much.
Absolutely. Anthony.
So yeah, I wanted to ask, but I think that should be because I'm actually on my phone. So I want to know the assignments, is it contained in the repository?
Yep.
Okay.
Yep, absolutely.
How do we submit the assignments?
Oh, actually, so for this first assignment, it's going to be actually for you to try at home to write a computer program in a language you do not know.
Okay.
And it could be anything. And we'll just be asking you to share back. Later on, there'll be some homework assignments that will help you, that'll be specific that you might want to bring back. But for this first one, this is really to explore, watch those 3 blue, 1 blue, 3 brown, 3 blue, 1 brown video. And the other is to write a computer program in a language you don't know and then learn about that language.
Okay. Thank you.
Yeah, absolutely. Umair, and you'd asked about the recording. The recording will actually be coming out after the recording is done. So it'll need to transcribe, and then we'll need to and then we'll put it in the replay. Great. Other questions? Oh, Anthony, do you have another question? Okay. You're very welcome, Janelle. Other questions? Well, Abby, let me ask you this. Is this sort of beginning to gel a little bit? Is this sort of making sense now that it's a very broad overview, but.
Yeah, what I'm really interested in is, hey, Anthony, do you mind muting? Thank you. Yeah, what I'm really interested in is I work a lot with teachers who are working with, it's called SIFE, Students with Interrupted Formal Education. And what I'm having a hard time, and I work with high schoolers, and the project that we're working on here, I'm like the least fluent in all of these types of things, but I am the one that communicates the most, not the most, but I communicate often with teachers and also students. So I'm trying to think about how, because a lot of anxieties teachers have are kids are smart and they're starting to use ChatGPT to support them, but it's not, the teachers don't understand what's really happening with it.
Right.
And so I think kind of the first start there is to think about, to kind of start from the very beginning about how old these kids are, what their proficiencies are. So that's probably the data I'm going to use. And I have a bit of anxiety about maybe I'm going to go through public data as opposed to our research data, because I'm sure you've heard this, the anxieties around what happens to our data once it goes place. Even if they're de-identified, it's what happens to it. So
Absolutely.
Yeah, but
so the interesting thing is, even for sensitive data, there's capability now of training, doing fine tuning on your own model locally. So,
okay.
And we'll be talking about that week 2 and week 3. So depending on what machine, so if you have an M1, M2, M3 base Mac, or M4 when it comes out, depending on your resources, you could actually train something completely locally. You wouldn't be able to train from scratch, right? But you would take a pre-trained model like now Llama 3, 8 billion parameter, or Phi, much smaller, And you can train it to do things. So, and we'll, by the end of this course, you'll understand how to do that. Also, Vanderbilt does have secure ways of inferencing on data. So you can securely inference on, you can use GPT-4 securely, so you're not sending the data off. So that's good. But if you need to train a model, then we'll be covering how you can do that in a secure and safe fashion.
Awesome. Oh, I had another thought, but I forgot. It'll come back to me and I'll raise my hand, but I don't want to take up till.
Sure. Anthony, did you have another question?
Yeah, so mine is more like not necessarily a question, but I want to understand, like, okay, so my background is in healthcare and life science. I'm a pharmacist back home in Nigeria before coming to the business school. And my goal is to solve problems in healthcare using AI. So I have like quite a little ideas here and there, but nothing concrete yet. So when I saw this program, I was like, okay, let me begin to get my hands dirty, learning about generative AI, prompt engineering, and all that. So how would what would I focus on in this program, and how would this program help me to achieve that?
No, that's great. I think this is you've joined at a really important time. 2 days ago, MedGemini was released. MedGemini is a very long context model. We'll be talking about that is multimodal and had extensive training on healthcare data, not just text, but images, EEGs. And so, Abby, actually, we need to figure out how Gemini was trained on the EEGs. That's going to be important. So understanding how the models work and the different types of problems you can solve with them is going to be really important. So by the end of this, I think you'll have a very good understanding of how generative AI works, how the models got trained, and then all the different ways you might be able to use those models. Sometimes the obvious ones, asking questions about electronic health records, all the way to the other, doing, business operations based on a model which understands more about medical, for example. So you could imagine, big thing in hospitals is room turnover. Can you predict when the patient is going to be out of the room? And is there anything keeping them from being discharged from the room? Can tell you if a patient needs to have any kind of physical therapy, you better get that in, because they can get backed up and that patient could be in the room another day or 2 days because they simply couldn't get into the physical therapist. So, now if you know that you have a pre-trained model, now you know what kind of questions to ask, and you can imagine even doing chain of thought. Given this patient and their background, here's their record. Describe for me reasons why the patient may not be able to be discharged tomorrow. What are some actions that may be possible to take in order to, prompt engineering or training a model, or, there are so many different things you can do now that you have these models that are trained on healthcare data, including, hey, helping, treat them clinically. There's that too. There's the clinical side and the operational side both. Yeah, Abby, you remember your question?
Remembered my question. So I think one of the most productive translators I've ever seen, that actually takes in like semantics and like ways of, totally lost the word for it in English, but like colloquialisms, that's what I'm looking for. And it's called Deep L. And I'm just kind of wondering where that information is coming from, because that does also seem to be updating itself in real time, especially like with slang. So I'm kind of interested in if you have any insight into that program.
So the model is going to be, so the model needs to be trained on language, right? And you can imagine if there are colloquialisms which are very, very recent, if the model has not been trained on more recent, then it won't know that. You can do parameter efficient fine-tuning on models, and so it can learn those things. But can you think of a colloquialism that we can try out real quick? And we can just see how well the model does.
Sorry, I always hate when I do that. Okay, I'm gonna say it in English and just kind of see like what it gives us back in Spanish. It's essentially like I'm only thinking of like vulgar ones. So let me just think of one that's not vulgar.
No, right, exactly. Yeah.
Let's just do one in English that's like oh, okay. In Spanish, it's don't drown in a cup of water. Right. So
Okay,
it's essentially
let's try that one. There is a phrase in Spanish.
Yep.
Don't drown
in a cup of water.
in
Cool.
Okay. And now I can say, is there a similar colloquialism in English?
So I'm gonna make an assumption. I hope it says like don't turn a mountain into a molehill into a mountain.
Great, yeah.
So I'm just kind of
There you go.
Yeah, cool.
That's what the small stuff.
Cool. Okay. So that's really interesting. I'm just wondering, I don't know. Like, I guess I'm wondering, like, when it comes to like kid speak, are they pulling from like TikTok?
It could be. I mean, yeah. Colloquialism, you know. Man, I cannot colloquialism.
Really, I can't spell it either. And I write about it all the time.
Use nowadays.
Explain to me like I'm 50.
Right. Explain to me like I'm nearly 60. Don't freak out over nothing. Oh, it's trying to keep with don't make a mountain.
Yeah, okay. Well, okay.
Okay.
Yeah.
You know, so you can get the idea, you know, that actually a lot of that subtle meaning is there, and the cool thing is that you can do it in any language, right? Because it's the concept. So it's able to translate, not because it's literally translating. Instead, it was here in the space.
Right.
And here is the concept of, you know, don't drown in a cup of water. Don't get too worked up. Okay, now what are the things that are close? Well, this is close in English, Spanish, Arabic, you know, in any language that it knows, it's going to be doing that conceptual matching.
That's really cool. I'm also just interested in seeing how this like kind of works with literature too, because that's been a really difficult thing. And I guess I'm wondering, like, I know I'm kind of getting into like the touchy-feely stuff, but that is my area of research. I also think about if we're talking about cultural differences, how that makes sense of it. So those are just like the big questions I have, especially try to rebuild a new curriculum, like not rebuild a curriculum, but build more curriculum for students.
As one of the things that we're going to be doing as part of Translate, of course, is we're going to take that entire curriculum.
Oh, you're working on this with us?
Uh-huh.
Oh, yay. Okay.
Very long context model, but the entire existing curriculum for a particular book there. And then put the entire other book and say, now redo this curriculum on this resource.
Okay, cool.
I mean, can you do it all at once? Can you do it piece at a time? What would it look like? All that we're going to have to figure out what that would look like. But we do know that long context models, you know, the longest ones that we have easy access to right now are about 1 million tokens. So it's it's a decent size. And remember, the models have equal access to everything there and can reason across that long context. So we're going to explore the limits of how far it can go. and what kind of additional guidance do we need to give it in order to explore.
Cool. We don't have to talk about this right now, but I didn't realize you were working on that with us. I'm really excited. If you have any questions about like just like the whole theoretical part of like translanguaging.
Oh, tons. Yeah.
Oh, okay. Okay.
Yeah. We'll be kicking off that work after, we want to make sure everyone could, sort of get this sort of grounding, and then yeah.
Thank you so much. I appreciate your time. I'll see you Wednesday.
See you Wednesday. All right. Any final questions?
See you Wednesday.
See you Wednesday. All right. Take care, folks.
See you on Wednesday.
See you. You're very welcome. See you, everybody.